Okay, recording is rolling. It is Monday, April 7th. So we have a lot of exciting stuff lined up today. Before we get to that, last time I told you guys back on Friday, you guys were doing an in-class quiz, electricity. So here's top scientist list. This is for all my honors classes. And then, so if you're doing the same set of demos today for my conceptual classes, they had a little bit different quiz. So there's my conceptual classes, top scientist. There we go. Top scientist, top scientist. So awesome job if you made that list, top scientific for electricity. All right, so we're gonna switch over to magnetism. So I'm picking up from last 2 weeks. It's like, well, how do you generate an electric current? Well, if there's a voltage, but how do you get that from, say, like non-permanent magnets? Or if you have a magnet, how do you get a current out of that? All right, so we're gonna bring in some magnets today. So a little bit different organization I'm trying for today is I have some demos I'm gonna put together for you guys. I've got a bunch of items just within reach right here. Okay. And actually, this is also my plan tomorrow. Tomorrow, I'll give you guys all the materials that I'm about to use to put together all these, and then have you guys put together all these things too. Okay. I have a stack of posters. We'll go through the posters I haven't got through yet, so related to electromagnetism and a couple other things. And then I have some demos for you guys, some video demos, including some Paul Hewitts and some other ones too. All right, so that's the plan. So first, these things. How do you make, well, top of list, compass. How can you make a compass? So I do have some permanent magnets here. Here, look at some magnets. Now you have to know, see, how does a magnet work? So how many poles are on a magnet? Yeah, 2 poles. Right. Guys, is there any such thing as a unipolar magnet? Maybe that only has a north pole? Is that a thing? Nope. They're all a dipole, right? So all magnets have a north and a south, right? Now, tomorrow, when you guys get that, can I have like a whole case of these back there? So there's just a few of these I have, right? So you'll definitely get a stack of these tomorrow, right? And you have to know where the faces are, so you know how it's working. And so where the poles are in it, right? And the poles are on the faces. So one of the poles is right here on this face, and the opposite pole is on the opposite face. Okay, so one of these is the north, and the other is the south. Actually, I don't know which one's which. I just know they're opposite. So I'm gonna make a compass. I got a couple of glasses here. One has some water in it. One's dry. Okay, and I'm gonna take say 3 of these magnets and put them together. Now, when I put these together, let's talk about magnets a little bit again. Guys, what attracts? Does north and north attract, or north and south? Yeah, north and south. Right. Yeah. So when they stick together, even though it's 3 individual bar magnets, it effectively acts as one giant bar magnet. So one side is north and one side is south. Okay. Right. Then I put these down so that the poles are faced horizontally. You see the poles are faced horizontally, right? Right. They're not up and down. This way, right? So it's horizontal. Right. Then put this in this glass of water, and let's see what this does. Oh, well, nothing there. But what if I turn this like 90 degrees? See, it's going to go back to the original orientation. Or what if I turn it all the way backwards how it was? Let this go. Okay. You see, it's always trying to orient itself. See where it kind of comes to a stop. Kind of along this line right here. It's trying to get to this line. Okay. There's your north-south line. You know, that's for magnetic north-south. So we're in a really weak magnetic field right now. That's Earth's magnetic field. Okay. And that way is north. So magnetic, okay. So that way's north, and then that way south. Okay. Now, truth be told, when people were laying down the conventions for what side of a magnet is north and south, right, back like hundreds of years ago, they didn't know that, okay, north attracts to south. We know that now, but they didn't back in the day. They got the convention backwards. Oops. So technically speaking, Earth's south magnetic pole is up in Canada, and Earth's magnetic pole, north magnetic pole is down in Antarctica. So it's kind of backwards, but it's right. Right. And then the magnetic north south don't even align exactly with geographic north south, so a little bit different thing. There you go. So there's a compass. You guys get to build that tomorrow. Let's water off. All right, what's next on the list? Ooh, electromagnet. So throughout the day, you'll see the principles of how these things work. Right, it's a little bit different perspectives, but up at the front, I'll put these things together so you can just see it working. Okay. What I have here, I have a bullet with a wire wrapped around it, and most of this wire is insulated. That's all the red insulation. Okay? But I have stripped the ends. No, because I'm going to tell you guys something today, and I'll tell you tomorrow. And this is a safety thing. So, guys, everybody listen up here. Everybody definitely paying attention right now. Right. So when I give you a wire tomorrow, maybe the ends are stripped, but maybe not, and then you'll have to strip them. And if you do, there's a right way and a wrong way. So you'll have these big old scissors right here. Now, guys, here's what you do not want to do. Guys, do not do this. because I've seen students try to do this, so many times in the past. It's like, don't, yeah, okay, I gotta strip this wire. Kind of like, bam, bam, bam. That's really, really dangerous for this reason. Okay? There's a lot of resistance here, and then you don't know when it's gonna snap, and then it snaps, and you got these big heavy blades, and all your friends' eyeballs nearby, and that is a bad combination. So instead, the correct way to do this is to go around, just make a very careful incision. Go around, around, around. Just cutting the insulation, not the wire itself. Okay, and then here's when I got started from. Okay. And then just pull this; it'll just pull right off really easy. Okay, so that's the property that I'll probably show you guys that tomorrow. Also, in case you have to strip any wires, right? So you just want to make very careful incision, then put the scissors down. Right, you're done with the scissors, and the insulation will just pull it right off. Okay, so see, most of this is insulated, so if there was a current going through it, it would be forced to go through the wire itself. It's not going to route through the bolt. Okay, but the ends are stripped, and what can I do with this? Let's see. Can this do anything? Can I pick up this paper clip? No. Now this paper clip does have iron in it, which is ferromagnetic. So I mean, I could set up the permanent magnet, so that works. Okay, but not this bolt, at least not yet. But watch what happens when I take this battery and I connect it to these leads. That's all gonna change. Lead. Oops, got a good connection there. There it is. Yeah. Oh, look at that. You can pick up that paper clip right there. Okay. And then when I disconnect the battery, boink, paper clip falls off, and then I can't pick it up anymore. Okay. So okay. So something to do with if there's a current flowing through a wire that's coiled around, it can turn into a temporary magnet. It's called an electromagnet. That's interesting. Hold on to that idea. Next thing I want to show you guys. All right, motor. Now this is the trickiest one to get work. Some classes this has worked really well, and in other classes it's been kind of spotty. So let's see if I can get a good recording in front of you guys here. But I need a stack of magnets. Now for this one, let's see, I got a couple of these ready to go. Got these coils of wire. Okay. Now notice, of course, it's mostly insulated, except I got the end stripped. Right. So, right now what? And notice how it's balanced too. Do you guys see how it's symmetrically balanced? So, like, if you draw a line between these two leads, it goes through the geometric center of that circle. You guys see that? Right. So that if I was balancing this, it doesn't really have a strong preference for which way it wants to hang. I mean, maybe a little bit that way, but not a lot. Right? Okay, so that's going to be a really helpful tip tomorrow. One of those little subtle tips. Right. Then take a couple of paper clips, put these on the ends of the battery. Right. So it effectively extended the leads of the battery. If you want to take those down tomorrow, that could be helpful maybe. Right. Right, so make the connection between the paper clip and this wire. Right, put this over the magnetic field. Oh yeah. Yeah, you guys see it spinning right there? You guys see it spinning? Okay. Okay, got it going. And guys, how long could that spin for? It could spin until what? Yeah, until the battery drains. Oh, it was going. All right, on and off. So. There it goes. Yeah, you guys see it spinning. Right. Yeah, that could go until the battery drains. That's pretty good. It's pretty good right there. Until the battery drains. Right. Because that's the source of energy, which is finite. Right. There's somehow the energy is being transferred, see, from the battery and chemical bonds until electrical energy that goes through this. Right. And then because it's in the presence of a magnetic field, that's turning back into mechanical energy. That's different. Didn't see that last week. Right. And then so last one. The opposite of a motor is a generator, or really it could be the same device. It's just doing the exact opposite process. Right, so I got this right here. Right, so I've got this hand crank. So some kind of input mechanical energy from my hand, right, forcing this to turn. And inside all this, there's a wire that's being forced past the magnet. And I have a little light bulb here. So give us a cranking. Guys, watch this light bulb when I crank this. Ooh, look at that. Turns on light bulb. Right, there's a monster. Okay. Right. And I have a really similar one right here called a Faraday flashlight. Same principle. There's a big old neodymium magnet right there. You can see this shaking back and forth, moving past this coil of wires. Right. So check this up. Right. So right now there's mechanical energy from my hand going to make this magnet move back and forth past this coil of wires. It's being forced past. Okay. Now there's no conventional battery anywhere inside this flashlight, but there is what's called a capacitor, and we'll be looking at those later today too. So it's storing the energy, not in the chemical bonds like a battery, but and the capacitor will store it in an electric field, kind of like the Van de Graaff from last week. Turn that. Oh, look at that! All right, you got some light right there. Got some light. Turn that off. Okay. All right. So there you go. So what's the principles behind all those, and how are they all tied together? Okay. Everything you saw. Well, let's look at some posters and see if we can make some connections here. So you guys see this last couple of weeks, we've been mostly working with these two, right? We had some battery voltages going on here. We had some resistors going on over here. Right? That's mostly been our focus. So I got some new ones for you guys today. I got capacitors and inductors. So I'll show you guys the posters now and then video demos later. Okay. So let's look at this. Capacitor, first one here. So the two parallel lines, that's the symbol for it on the schematic. And what it is, it's literally just two parallel plates. Now, if you run a current through, then there's going to build up a static charge, and that can store some energy in an electric field. Right? That's what's in this Faraday flashlight, so that when I shake it, I can turn this on 5 minutes from now. It'll still hold some of the energy. Okay? So capacitance, you could have charge per voltage. The energy stored could be 1/2 capacitance voltage squared. Okay? Of course, you can store energy in this temporarily. If you find some old appliance and you're pulling apart with a screwdriver, like, oh, here's an old TV set from the 1990s. It's not plugged in the wall. That can hurt me, right? But you got to be careful because they'll have capacitors. You can still get a pretty good shock, right? It could be pretty dangerous. Okay? If you have one of these in your circuit, what does it cause the voltage to do? It causes the voltage to lag. So you hit the on switch that closes the circuit, bam. It takes a while for the voltage to build up. You hit the off switch, opens it up. The voltage doesn't disappear right away. It takes a while for it to dissipate. That's what this graph's trying to show. It's just like the voltage lags behind the current. Okay? If you have multiple capacitors in a circuit, then it turns out that the rules for adding capacitors together are exactly opposite of what they were for the resistors. You guys remember two resistors in series? You just add them up, and in parallel, you do product over sum. You guys see the rules are backwards here? So in series, you do product over sum, and then in parallel, you just add them up. Okay, so that's kind of interesting. Okay. I'll show you guys a video demo of this later. Some kind of lightning jar. Okay. All right, what else can I have on here? Inductor. Now, what's an inductor? Well, the schematic symbol is just draw a little curly right there. Okay, so curly going on. It's going to be this inductor. And that's really else. It's just literally a wire that you coil into a coil like this. So this right here. So all this red wire could be an inductor. Okay. And that will cause current to lag behind voltage. So if you have one of these in your circuit, you flip the on switch to close the circuit. What if you also have a light bulb in the mix? The light bulb will not turn on right away, and it'll slowly turn on. Right, but it'll take a while. And then if you hit the off switch, open the circuit, turn it off. Right, well, the light bulb still stays lit, and it takes a while for the current to dissipate. So it'll get dimmer and it'll slowly turn off. Okay, so that's what you see here. So inductance, it's voltage over rate change of current. So some kind of rate change. You can store energy in a magnetic field. So this is U as energy. So 1/2 times I times inductance times the current squared. Okay, so store energy temporarily. And if you have multiple inductors in a circuit, then the rules follow exactly the same as the resistor rules. So in series, you add them up. In parallel, you do product over sum if you have two of them. Okay, so there you go. Inductors. Got a video demo for that later. Look at that. All right. This right-hand rule here. I don't know if you guys remember vaguely, but back a long time ago, I showed you guys a different right-hand rule for torque. Right? I don't think we did a whole lot with that because anyway. But there's a different right-hand rule for it's going to tie all these electricity variables together. First of all, what are these variables? I bet you guys know at least some of these. Because what does F stand for in physics? Force. Yeah. What does I stand for? Electric current. Yeah, which would be measured in amps. True. Yeah. So force in newtons, electric current in amps. Okay. Now, I'll tell you guys, L is like a length of wire. I'll get back to that in a minute. Right. Now, so like if you have a wire that's like so many meters long. Okay. What do you guys think B stands for? And it's something that doesn't actually start with the letter B. What do you think D is? Magnetic field. Aha, that's it. Magnetic field. Right. Like how strong is a magnetic field? And you can quantify that. So there are different ways to do it. One way is in how many Tesla, right? So like how strong is this magnetic field? Earth's magnetic field, which we're all in right now, is like 10 to the -5 Tesla, something like that. Okay. So what right-hand rule says is if out of these three, magnetic field, electric current, and a physical force, if you have any two of those lying around, and they have some kind of perpendicular components to each other, then the third one will pop up almost by magic. Okay? And that actually explains a lot of the demos that you guys just saw in the last few minutes. So here, I'll go through those again. Let's start with, what if I force a current into a loop? That's what this was. You guys remember when I attached the battery right here and I was like going around picking up paper clips? Because that turned this into an electromagnet, didn't it? Oh, so that's where the magnetic field was coming from. Right? See, when it was all disconnected, there was no magnetic field. But when I was forcing that current into a loop, I was getting a magnetic field. Actually, just by having a current going through a wire, there's already a magnetic field that builds up around it. But when you loop it into a loop, it straightens it out, so it turns into a bar magnet. Right? So that's an interesting take from this one. How about, what if I have an electric current and I put that next to a stack of bar magnets in magnetic field? So I have a current going into magnetic field. Okay, that's what this was when I had the battery with the leads, and I had this right here. That was a motor. You guys remember it started spinning? Okay, so because it created a physical force. That's what a motor is. It takes energy from in the form of electric current, right? And it turns it back into a physical force. Right? And the third thing I can create from this is, what if I force a wire past a magnet? That's what this is right here. If you force a wire past a magnet, okay, it's going to generate an electric current. Right? And that's how power plants operate. As at the point of a power plant, you have a giant turbine. It's maybe turned by steam because you were like heating something up. Maybe you're burning coal or something. Anyway, you get a turbine to turn somehow, one way or another. Get a turbine to turn, right? And you're forcing a wire past a magnet. Shoot, shoot, shoot. Right? And that will generate electric current. That's how you transmit. So yeah, and the fact that it's a right-hand rule in contrast to a left-hand rule or any other kind of rule tells you the directions of these things. So force, of course, has a direction. Current has a defined direction. Remember, it's like flow of positive charge. Remember, back in the 1700s, they accidentally got that convention backwards. Oops, we're stuck with that in the books. Right, so we're still right-hand rule. So I guess the electrons are actually flowing this way. Oops. Right. And then magnetic field, the convention is you draw the lines going from north to south. So if it was south to north, maybe this whole rule would flip the other way. Maybe we have a left-hand rule, but we got a right-hand rule. So there you go. Right, tells you exactly how those vectors are aligned. Right, you guys good so far? Right. Faraday's law. So speaking of power plants, how much voltage can you create by running a wire past a magnet? Right? Well, if you have a loop of wire, say, that looks like an inductor, right? And you run a magnet in and out of that. Paul Hewitt's going to do this later. So when you see Paul Hewitt do this, remember this one. Okay? This is how much voltage is created. Now, I usually been using capital V for voltage. A lot of physics textbooks use Greek letter epsilon, so I figured just to change it up so you guys could be familiar with that. This epsilon stands for voltage or potential difference. Same thing, right? N is the number of coils. So if you have more and more coils, you can get more and more voltage. And this right here, this is Greek. Does anybody know what Greek letter is that right there? It's Greek letter phi, right? And in this context, it means flux. And okay, so what is that? Right? Magnetic flux is if you take the strength of this magnetic field, some number of Tesla, and multiply it by this area and this coil of wires, and you get some flux. And the d over dt, that's calculus notation for a rate change. Okay, so so some kind of motion involved, right? So you have this flux turning on and off. You multiply that by the number of coils, and that will tell you how much voltage is created. Right? That's it. All right, guys, good. All right. So what's a generator? What's a motor? They could be physically the exact same device. They're just transferring energy in the exact opposite processes. So a generator, you're taking mechanical energy, turning it to electricity. A motor, you take that electric current and turn it back into mechanical form of energy, right? So through this process. So, I mean, the energy is coming from somewhere. This whole process, energy is conserved. You're never creating energy. You're never destroying energy. You're just transferring energy from one form to another. So I got this waterfall. Maybe it's forcing the paddle wheel to rotate. And that's forcing this wire to turn past the set of magnets. Okay, so it's moving in and out of the magnetic field. So that's transferring the energy onto the electric grid. Okay, now the energy is on the electric grid. Okay, then maybe in your home, you have this electric current runs past another set of magnets, which you guys saw earlier today. What happened when I had this wire past this magnets? This thing started spinning because that was a motor. That's all a motor is. Right? Run a wire past the magnet, electric current going through it, it creates a force. And if you know which way the current's going and you know which way it's north and south of the magnet, you can use right-hand rule to predict which way this is going to rotate. And then your ceiling fan runs. Okay. like I said. And oh, inductive coupling. So this you can use to increase and decrease the voltage, right? So here, it's like this. The device is called a transformer. The principle is called inductive coupling. Let's say I have an electric current on this red wire on the left side. And you guys see a bunch of coils, right there? Right. And then across this transformer on the right side, maybe I got an otherwise completely separate circuit set up over here. You guys see not as many coils on the green side? Not as many coils. Okay. So if you're transferring electricity from the right side to the left side, this would be stepping down the voltage. Right? And this formula right here tells you exactly the proportion. Okay? So the voltage drop is exactly proportional to the ratio of the number of coils. Okay? For example, okay, suppose you have 100 coils here and you have 50 coils here. Guys, 100 versus 50, isn't that a ratio of 2 to 1? Okay. So what that means is that the voltage is also going to step down by that ratio. So if on the red side you had 240 volts, on the green side you would have how many volts? 120. Yeah, because if you have half the coils, you have half the voltage. That's all this says right here. Right now, because of conservation of energy, that also forces current to change too. Right here. Oh, write down why. Do you guys remember Joule's law? There, it's down. So Joule's law says power is equal to current times voltage. Power is in watts, current could be in amps, voltage could be in volts, right? So now, since energy is conserved during this whole process, you're not gaining or losing energy. Okay? You think of that sort of like power being constant, right? Which is a rate of energy. So it's that connection, right? But if you're stepping down the voltage, what has to be happening to current? It has to be doing what? Also going down or going up? Going up. That's right. Right. So here's a multiplying example. Let's say 24 was like the power, 24 watts, whatever. Right. So 6 amps times 4 volts. Well, you know how else do you get 24 watts is doing 8 amps times 3 volts. Right. So by the voltage stepping down some amount, the current has to step up. Right. And that's what this box says right here. So if you're going from left to right, if you're stepping down the voltage, at the same time you're stepping up the current. Okay. Now, since electricity visible, can't really see it. Where this really makes sense to me is if I do a water analogy. So let me give you guys a water analogy. Okay. You guys remember, I think I told you guys this the other day too. This is why we use alternating current to for our power grid, is because it's easy to step up and step down voltages. Okay. And why would you want to step down voltages? Well, let's look at a water plant. Guys, this water plant, do you want to route the pipes to everybody's houses individually, and then people are turning on and off the faucets, and then the current is completely erratic and it's start, stop, start, stop, start, stop. That probably doesn't sound very good. But what if you just instead, what if you pump all the water into a giant water tower and then route the water tower into everybody's houses? Now, if people are turning on and off the faucets, all that's going on inside the water tower is the water levels just going up and down a little bit at a time. And you keep getting replenished from the water treatment center. Right? That makes a lot more sense, doesn't it? Right? Well, just replace the tall water tower with a high voltage, and now you have electricity. So those electric lines out there might be like 100,000 volts. In this room, these outlets are like 120 volts. Okay. Okay, so we're going from like thousands of volts to maybe like 100 and some volts. Okay, so you want to step the voltage way down, and in turn the current will increase. Okay, so very low current, high voltage on the power lines, right? And then a low voltage but a higher current, say like inside this room. Okay. Right, and then yeah, up on here. Okay, I think you guys saw this the other day, right? Alternating current. Right, 3 phase alternating current, spin a magnet, pass the wires, generate some voltage. Okay. Here, one more thing about power lines. I meant to mention this. Let me go fill into detail, right? Because I need to bring in the application of this L right here. So suppose you have a power line that's running east-west. It's got some current flowing through it, maybe like a few amps, and it's in Earth's magnet field, so like 10 to the negative 5 Tesla, something like that. Okay. Let's say this power line's, I don't know, 20, 30 meters long. If you multiply all that together, how many amps times how long is the wire times Earth's magnetic field, okay, there's actually a small force. It's a tiny force, but it matters a little bit, right? So the wire is actually being pushed to the side a little bit. So fun little trivia there. All right, so I got next here. I did demos for you guys, which you're going to make tomorrow. Did all the new posters. Okay. Now it's video demo time. So we'll start with capacitors and inductors, and I'll eventually get to Paul Hewitt. So capacitors. All right, first you remember how capacitor is two parallel plates? Now he has a cylindrical version of that. You see that? Like these two cylinders. Now watch the spark. And bam, spark. You see that? So he's showing that it's all charged up. And then he just goes back and recharges it. Kind of like you guys remember last week you had the Van de Graaff you guys were playing around with a little bit. Okay. And then oh here it is again. Bam, spark. Bam. Okay, so he's charging up. Right? Ben Franklin and friends used to play around with these. They call them Leyden jars back in the day, Leyden jars. Now he pulls it apart. Now I've got him muted, but what he's showing here, he's going to touch the two metal cylinders together. There's no spark at all. But when he picks up that plexiglass separator, he says it feels all prickly. So he's trying to show that the charge actually is held in that plexiglass separator, not on the metal parts. All right. So it's just that. Okay, but that's a capacitor. So you can store energy in the form of an electric field. Again, sort of like a battery, but it's not a chemical reaction. It's just a charge. Okay. All right, so got some animations showing how this Leyden jar works for this capacitor. Okay. Got another guy here has some called ultracapacitor. Right, so got here. Oh, here's 2600 farads. Farad, I mean, there's a way you can link back to metric system. I couldn't tell you right now, but some combination of like amps and meters and newtons or something like that. Right. But here's a really big capacitor on just a normal circuit board. And notice this is in microfarads. Do you guys see microfarads? We're going to go to ultracapacitor, which is some number of farads. Actually, it's like thousands of farads. So it's like a billion times the capacitance. So even a big one, right? And throughout this video, he fries a bunch of stuff. And he's frying a coin here. Right. Again, it's a bunch of energy all released at once. Okay? And then I'll do some math. Right? So yeah, I just want to kind of breeze through this. But you guys see, so energy stored is 1/2 capacitance voltage squared. Does some math right there. Shows you how much energy he's talking about. All right. Okay. Yeah, adding capacitors together. Right. That's some other things. All right, but let's breeze through this. All right, let's look at inductors. Inductors. Oh, look at that. It's just a coil of wires. So there's some different inductors. Right. Add a coil of wires up here, inductor. Okay, so what's that good for? What are we doing here? Okay. Now remember how with it's not gonna let me. Oh, here it is. All right. So if you have a current going through a wire, it'll naturally set up a magnetic field around it. That's that blue line right there. Actually, later on today, Paul Hewitt's gonna show you guys this with a really cool demo with compasses. So be on the lookout for that. Right? But then if you coil the wires together, right, it effectively straightens out that magnetic field. Right? Okay, there's your electromagnet. Like I was showing earlier, I can pick up the paper clips with that right there. Right? Right. So what else can you do with this? Okay, if you have one of these in your circuit, it causes current to lag. So if you hit the on switch, it takes a while for current to build up. And if you hit the off switch, it takes a while for the current to dissipate. Right? So if you have a light bulb in the mix, it'll dim right after a while, right? And eventually turn off, but it takes some time. Okay. Also, because the fact that it creates a magnetic field, you can create a inductive coupling with this. You guys remember earlier today, I was showing you guys that transformer where the green wire and the red wire weren't even touching, but they were transmitting electricity. So you're going to see that right here. So, all right, so looking at this inductor, you guys see there's two separate inductors. There's one on the bottom of the screen and one on the top of the screen. Right? Now, let's say the bottom one has an electric current actually running through it. Well, if that's generating a magnetic field, do you guys think that top inductor is picking up that magnetic field? And that's in turn inducing a current, right? And then here, play this a little bit. Okay. So see how it's getting closer, further away, closer, further away. I wonder what that's doing to like the voltage and the current. Hey, look at that. See, it's getting stronger, weaker, stronger, weaker. Kind of makes sense, right? Next one here. More inductive coupling. So you guys see that big old voltage source in the back, the big black box? It's going to flip that on. Pow. Now, oh, that little LED just turned on. Now there's an electric current running through this big copper ring. I'll call it copper in it. What about this on the right side? Look, it's got a light bulb. Pow. You guys see you plugged in that light bulb and just turned on? Right? Now there's no battery on the right side. There's no energy source. Okay? So how's the light bulb turning on without it? Right? Because whatever current's going through this big copper ring on the left side, that's creating a magnetic field. This ring on the right side is picking up that magnetic field. That's inducing a current, and it's going to turn the light bulb on. So that is wireless transfer of electricity. If you have anything to do with like a wireless charger, I don't know if anybody has anything quite like that. No, maybe. But well, future's a long time, so if you ever charge anything wirelessly, it's going to involve these inductors. Right? Get this inductive coupling, wireless transfer. Notice when he turns it 90 degrees, the light bulb completely turns off. You guys see that? Because then those vectors aren't aligned and the magnetic field can't transfer and no current's going to flow. Right? Okay, so it has to have certain orientations of those. Right. Ooh, let's look at this induction heater. Induction heater. That's fine. Right. So there's something called Lenz's law. So big old copper pipe, big strong neodymium magnet. Now, have you guys ever tried to pick up coins with a magnet? And you can't do that, right? Okay. So like pennies. Now, if you get a penny before 1982, it's mostly copper. Modern day pennies have a little bit of copper. I think that copper plated on the outside, right? But it doesn't matter. Anyway, you can't pick it up. So he's just showing at the very beginning that there's no magnetic attraction between those two. Okay, goes like tap, tap, right? There's nothing, tap, tap, no magnetic attraction. But watch this. If he drops the magnet down in the chain, look, there's some kind of resistive force that keeps it from falling away through, even though it doesn't actually attract magnetically. It's not a ferromagnetic attraction. So what's going on there? So as the magnet is moving past that coil, and it has to be a complete loop to make this happen. If that copper ring was actually a C shape and wasn't closed, this wouldn't actually work. So you need the full loop to make this happen. Okay. As the magnet's falling down, it's generating its own electric current in the copper ring. That's called an eddy current. And that eddy current, in turn, creates its own magnetic field, which resists the original magnetic field from that neodymium magnet. Okay. So so there'd be a resistive force. And if you put those two objects nearby each other, they do not want to move relative to each other or take some force to get them to. Right? That's actually consistent with conservation of energy at a power plant, because if that did not happen, then you wouldn't be transferring energy onto the grid. Right? So you got that. I have a simple motor for you guys. Okay. So magnets, battery, wire. Now, it's really hard to construct this exactly right. Some students in the past have tried. I mean, if you want to try this tomorrow, but I'll have you guys create the simpler motor like I was earlier. Right? But, oh, look at that. Right? So you got it all there. Got some current going. You got a magnetic field, and do you guys see us rotating clockwise from top? Clockwise. What do you think would happen if you flip that battery upside down? Go counterclockwise. Or what if you left the battery there and you took those magnets and you flipped the magnets upside down, reverse the north and south? Would that also change the direction? Yeah, because this all comes back to right-hand rule. See, all he did, he didn't give it a flick or anything. All he did was he just very simply set it on top and just let it go and just do its own thing. And it just naturally started turning in that direction. Right. So that's a basic motor right there. Right. Yeah. If you reverse the direction of any of those things, the current, the magnetic field, it's going to reverse the direction of the force. All right. We're finally up to Paul Hewitt. It's going to tell you guys some stuff about electromagnetism.
The source of that magnetism was betrayed years ago, more than 150 years ago, by a fellow by the name of Hans Christian Ørsted, who was a professor type teaching. I believe he was in a high school classroom. And he was showing the students that there's no relationship between magnetism and electricity. The physics books at that time had electricity as one subject and magnetism as another. And Ørsted was showing there's no relationship between the two. And one of the things he would do is he would line up the piece of wire like this and put it over a magnet, pass a current through it, and you really don't see anything happening. There's no interaction. But after class, a student came up and held the wire in this direction, and when a current passed through it, okay, watch this, when a current is passed over the wire like this, boom, you see that interaction? It turns out there's an interaction between a current carrying wire and a magnet. And it turns out, to make a long story short, the source of all magnetism is moving electric charges. And when the charges move through the wire, they set up about the wire a magnetic field. And that magnetic field is in concentric loops around the wire. If I pass this wire through a hole in a piece of paper, and I put a whole lot of little compasses around the wire, and no current goes through, all those compasses would point north. But you know what would happen if I put a current through that wire? All the compasses will line up with the field. And it turns out that field, it takes the shape of concentric circles about the wire. The further away you get, the weaker they get, but the direction is all that way. So surrounding every current carrying wire is a magnetic field that takes the direction of the concentric circles. I want to show you something that's even more interesting than what we've seen. Let's take this magnet. I'm going to put the wire in the magnetic field of this magnet, and I'm going to touch this momentarily so I get a pulse of current. And when I do that, when a current goes through this, would this wire, in a sense, be a magnet? How about when no current goes through it? It's copper wire. Copper is not ferromagnetic. Copper, you've all tried when you were a kid to pick up a penny with a magnet. It doesn't work, does it? Because the penny's copper, okay? So the only way you're going to get magnetism with copper is to have electrons flowing through it. Electrons flowing through anything would set up a magnetic field around that anything, yeah? Let's see what happens with the magnetic field of the wire and the magnetic field of the magnet. Let's see if there's any interaction. What do you suppose? Watch this, gang. You see that jump down? See that jump down? Let me turn the magnet around. Jumps up. Did you see that? I'm going to do it one more time. Watch. Wow, jumped up. So one way it jumps up, and the other way, put it this way, it jumps down. I wonder if that jumping motion could be harnessed. How many people say, well, no, there's probably no practical application of that. Wires will move in magnets. Big deal, right? Is it a big deal? It's a very, very big deal. Because guess what this underlies, gang? Electric what? Begin with M, end with odors. Try it. Motors. Any electric motors be working on such principle, okay? And dig this. Whenever you see any electric motor, realize, you know, sometimes we see things and we're so overwhelmed with the complexities, we don't know what the nitty-gritty is. Realize the nitty-gritty of an electric motor is simply a current-carrying wire, boom, being deflected in a magnetic field. Period. That's it. This was done by a couple of physicists about the same time in history. One was Michael Faraday, a Scottish guy in England, and the other was Joseph Henry, an American type in Vermont in the 13 colonies. And they both at the same time found the same effect. And here's what they discovered. They had meters similar to this at that time, but they didn't know how to get electricity. Well, they got electricity from batteries. A fellow by the name of Volta, Alexander Volta, Italian type, made batteries, and that was kind of nice. Everyone's excited about electricity. And then Michael Faraday and Joseph Henry discovered the following. No batteries over there again. No batteries, no tricks. Magnet, wire, meter. Watch this. You see anything? No. Faraday didn't see anything either. Okay. And but watch this. Henry didn't see anything either, but watch this. Did you see something? Again. My goodness. My goodness. There's no battery nearby, and guess what we are generating? Begin with EC. Electric current. I am generating electric current. And Faraday and Henry found out that. No batteries, no cells, none of lightning, none of that. Just the motion of a wire in a magnetic field. So Faraday goes to bed and he's really excited about that. And while he's in bed that night, I'm making this up now. While he's in bed that night, he's kind of thinking, gee, I wonder what would happen if I did it with 2 wires. So he gets up in the middle of the night, takes his candle, goes downstairs, had to do a candle. Little did he know that he was going to get rid of candles, honey. The candle industry was furious later on, okay? Because what he did is he went down and he took 2 wires. And guess what happens with 2 wires, gang? Twice as much current. Goes back to bed. Then he thinks, I wonder, 3 wires. Shall we try it? Didn't sleep the rest of the night, gang. I wonder, 1,000,000 wires. What do you think? 1,000,000 times as much. Okay, this is a remarkable discovery that one can, it turns out, induce voltage by simply moving a wire in and out of a magnetic field. And so Faraday's discovery is couched a little differently. Today it's called Faraday's law. And what it says is this, a little more complex. Change the magnetic field in a closed conducting loop of wire, doesn't even have to be conducting. Just change the magnetic field intensity in a closed loop, and you will induce a voltage in that loop. Now, this loop happens to be a copper wire, so the voltage in that produces a current. So look at this, you get a current. Change the magnetic field in two loops of that closed copper wire, two loops of that circuit, and guess what you get then? Twice as much voltage. Three loops, da. Well, that's the rule. All you got to do is change the magnetic field intensity and you will induce a voltage, which will produce a current if you're talking about a conductor. Ain't that neat? That is really, really nice.
And so then they started generating electricity. Is the next part. If you have one more call here, I'm gonna just summarize it. He talks about the electric sensors at stoplights. You guys, they use these all over in Vera, but I know sometimes I'll go visit my brother in Pennsylvania. They don't really have these, but here in Vera, you see them all over town. You'll see them. You guys ever see this pattern etched into the road when you're approaching an intersection? Look for it. You'll see them all over the place. And now, if there's a lot of traffic, then the lights are just timed to some timer. But if you're like, suppose it's 2:30 in the morning and you're like the only car on the road, and you drive up to the stoplight, right? What this will do by driving your big car over that has a bunch of iron in it, right? And it'll change the voltage a little bit, and then that'll trip a sensor, and then let the system know that your car's there just by changing the voltage a little bit. All right, let's look at magnetic field here. Magnetic field. So got a couple of bar magnets, okay, going toward each other. You threw a paper on top and then a bunch of iron filings. Okay, you guys see all those lines head toward each other? That's how you know that the north and the south are facing each other because they attract. Now, convention, by convention, we draw all the lines going from north to south. I guess how the arrows are pointing. Okay, just a coin flip. Could have come up with the opposite convention. That's what we do. So north to south. Okay, and that goes hand in hand with the right hand rule if you're trying to figure out like which way is the motor going to turn. Right, you want to know, right, north south line. Right. All right, so there's a bar magnet. There's a bunch of field lines. Now, okay, there's north and north. Do you guys see north and north? The field lines don't even cross each other. Ooh, look at that. Right, but then if you go north to south, they'll pull together. Right. All right. Let's look at flux because part of Faraday's law, that was that last Paul Hewitt you guys saw rolling. You're saying if you change the flux, that can induce a voltage. So what is flux? Flux is just this magnetic field, which is these blue lines, times some area that the field is going through. Oh, look, it's Greek letter phi for flux, right? So, okay, if you rotate the rectangle that way, it doesn't change the flux, but what if you make the rectangle bigger? Hey, look, bigger rectangle, more flux, because there's more area, right? Or a strong magnetic field could also give you more flux, right? And then here's an equation down at the bottom, right? There's one more part, which is that cosine theta. Do you guys see if you turn that area so that no field lines go through the rectangle, there would be no flux? So that's all, because that incorporates the cosine theta. You see that in the graph, right? Right. Okay, so that would be a changing flux. Ooh, what if I put a wire around that rectangle? That would look just like the motor I created for you guys at the beginning of class, wouldn't it? Right, okay, you go upside down, there'll be a negative flux, right? And then that whole thing can rotate in that magnetic field, and you could either be creating a force if there's a current running through, or if you forced it, like on a turbine, that would generate an electric current. So there you go. There's Faraday's law of motion there. What else I got for you guys? Let's go fast. Got some fun ones just in today. Right. When you think magnetism, most people think like ferromagnetism. There's actually different kinds of magnetism, and water is what's called diamagnetic. Water actually repels away from magnetic field. If you have a bowl of water, you put a magnet near the surface, you might barely be able to tell that it pushes the water down a little bit, depress a little bit. Those frog is made mostly of water, so put him in a strong magnetic field, he's going to be floating around. Right? He's just floating froggy day. Right? Or here, I got a strawberry version of this. Yeah, it's mostly water, right? Let's look at Earth's magnetic field. So Earth, of course, has a magnetic field. We've got a magnetosphere. That's why that compass worked earlier today. Okay. So here's an animation what this might look like from the side. So the sun's far to the left. It's sending solar wind from left to right. And here could be the planet like Earth. Okay. Oh, right. So, like one of the tricks to sending somebody to Mars is because it takes a few months to get there and a few months to get back. How do you protect your astronauts from the cosmic radiation? Right? Because on Earth we're protected by this magnetosphere. I see a little bit of cosmic rays seeping in the north and south poles. That's the northern lights. She got one of those too. The northern lights here. Right. And why does Earth have a magnetic field though? So the main theory has to do with inside the Earth. There we go. Inside the Earth, back 4.5 billion years ago, when the Earth was forming, a lot of the heavier materials, like the heavier metals, sunk down into the Earth. The mantle is molten. There's an enormous amount of geothermal energy there. Okay, so it's very hot, molten rock. Okay, and as the Earth is spinning, you get these molten materials, like a lot of iron is down there on the move. Right? It generates this magnetic field. Okay. Interestingly, if you look at the surface of Mars, there's a lot of water erosion all over the place, but Mars is almost completely dry today. So what happened? And the main theory is that since Mars is so much smaller than Earth, it cooled off a lot faster. When it cooled off faster, and it would have solidified, and so Mars at one time must have had a magnetosphere to protect whatever water was on it and protect its atmosphere. But when it cooled off and lost its magnetosphere, then it was no longer protected from the cosmic rays. So then all the cosmic rays just picked off its atmosphere, and whatever water used to be on Mars is now just evaporated into space. All right, so I think that's a pretty good pause point right there. Tomorrow, be ready to build a bunch of motors and electromagnets and compass.